In the last few minutes, I'm going to just zip by the statistical analysis that you can look at on your own. We've already done much of it. I did it graphically, but now I want to show you can actually do it analytically. And the basic idea is to write down all of the parameters that we described: size, power, the sample size, and so on. And under the null hypothesis, you can show that the probability of a type 1 error is going to be given by alpha over 2 being the probability of delta hat greater than c. And based upon this, you can actually calculate what the appropriate threshold is for deciding whether or not to reject the null hypothesis. And using that particular threshold, you can actually show that the threshold is going to decrease with the sample size. The more patients you have in your clinical trial, the more you can actually be a little bit more open about accepting or rejecting the null hypothesis, because you are more accurate about the data. And the threshold is going to increase with the volatility of the underlying patient response variable, as well as your particular statistical threshold. Under the alternative hypothesis, you can calculate the probability of a type 2 error. It's the probability of not rejecting the null hypothesis under the alternative hypothesis. And the alternative hypothesis is that, yes, there is an effect, and the effect is some multiple of the standard deviation of the underlying patient response, where kappa is some number greater than 0. And so I just leave it at kappa so you can decide how far away your alternative hypothesis is from your null. The farther away it is, the easier it is for you to be able to find a good drug when you're doing the test. And ultimately, what you're going to get out of this analysis is the sample size you need in order to achieve a certain level of power. So the power level that industry typically uses is anywhere from 80 to 90%. If you're looking for 80 to 90% power, that means 10 to 20% type 2 error. Then that will drive the sample size of anywhere from 1,000 to 5,000 patients. And here's a table that shows for standard numbers what it would look like for various different kinds of levels of power. So if your alternative hypothesis is only 10% of a standard deviation away from the null hypothesis, you would need something like 1,500 patients to be able to achieve a power of 80%. If, on the other hand, you have a much stronger treatment effect, in other words, the treatment that you've developed is really good and it shows extreme positive response, then you need a much smaller patient population in order to achieve a certain level of outcome. You remember in the first day of class, we talked about the drug Gleevec, which from the beginning of IND filing to NDA approval was 3.5 years. That was because in something like 30-odd patients, they had an efficacy rate of 100%. Everybody responded to the drug. So you don't need a lot of statistics when you see that kind of effect. The stronger the effect, the more you actually will be able to tell with a given amount of data. So the bottom line for understanding the risk of a clinical trial, apart from all of the other considerations we talked about, is how big is the treatment effect, and how that treatment effect scales is going to dictate the kind of financing that you're going to need. The stronger the treatment effect, the broader kinds of financing you can get. The weaker the treatment effect, the more risk-tolerant financing you're going to need. And so there's some very interesting things that we can do using proper financing to finance different kinds of trials. That's not something that's been really looked at in literature, and only now are business developers beginning to take notice of that.